cut off this one. So I skip to the end. The question is which element is being oxidized during the titration. And so gaining electrons is oxidizing. Oh my goodness. Losing electrons is oxidizing. Gaining electrons is reducing. And I assigned my oxidation numbers. Normally, oxygen is assigned a -2, but if it's in its pure elemental form, then it's a 0. And the rare times that it's a peroxide, a something 2, O2, then it's a -1, not a -2. Okay? So losing electrons is oxidizing. Okay. So this oxygen right here went from a -1, and then it turned into either this one, a -2, or this one, a 0. So if it was going from a -1 to a -2, that is gaining an electron, so I'd be reducing. But this -1 becoming a 0 lost a negative electron. That's oxidizing. So oxygen oxidizes when it goes from -1, even wrote a -2, -1 to a 0. That is oxidizing. Great. A precipitation reaction, number 28, is when aqueous things, liquid-looking things, make a solid, okay? So answer option A is not correct because, yes, we have aqueous things, but they don't make a solid. There's a solid on answer option B, but it's not on the correct side. We need to make a solid. The correct answer is D. It's when we take aqueous things and we make a solid, that's a precipitate. 29. In the equilibrium represented above, equilibrium reaction represented above, the species that acts as a base. Okay, reminder, Bronston-Lowry definition of acids and bases. So acids are going to lose hydrogen, bases are going to gain hydrogen. So let's see what happened here. This HSO4 becomes an SO2 minus. So this thing is going to lose an hydrogen, so it's an acid. Once it loses that hydrogen, then it becomes its conjugate, but the opposite, it's a base. Here, the H2O becomes an H3O plus. So this water is going to gain a hydrogen. That makes it a base. And then once it gains that hydrogen, that makes it the conjugate, and it's an acid. So which species are acting as bases? This guy is, and this guy is. So that would mean 2 and 3. All right, we have half reactions here. This first one, we are losing electrons. Leo, the lion, says grr. So losing electrons is oxidizing, so this is the oxidation half reaction. Gaining electrons is reducing, so this is a reduction half reaction. And we want to know what the coefficient is going to be in front of the aluminum when we balance these two half reactions, when we put them together. Now the important thing though is they have to have the same amount of electrons that are being gained and being lost. Because we have 3 electrons being lost and 2 electrons being gained, I need to multiply everything on the top by 2 and then everything on the bottom by 3. That way the electrons will cancel and then I can put these reactions together. In front of the aluminum solid, we have a coefficient of 2. Number 31, we got something, it's the same thing. We have 2 electrons being lost, 1 electron being gained, so I need to multiply everything down here by 2. And then once I do that, I can combine these things, right? Where the 2 electrons cancel, but everything else is there. So I need to have nickel solid on the reactant side with a coefficient of 1 in front of it. I need to have 2 silver plus on the reactant side, aqueous, so I can get rid of A. Okay, so now we're down to B and D. I need to have a nickel 2 plus aqueous on the product side with a coefficient of 1 in front of it. So that gets rid of B. And so then we're left with 2 silver, right? D. Okay, number 32. I have all this cool information, but I want to know what it's asking, so I'm going to jump to the end. I'll go back to it in case I need it. So the question is, which of the following experimental conditions is most likely to increase the rate of gas production? So there's 5 factors that make reactions happen faster or slower. Temperature, concentration, particle size / surface area, state of matter like a solid, liquid, or a gas, and then the presence of a catalyst. So the first answer says decrease the volume of the ethanoic acid solution used in the experiment. Okay, so if I have a liquid and I decrease the liquid's volume, and it's a solution, so a solution or a liquid, if I decrease the volume, I decrease the concentration. Like I take out half of the water, then it's a bad example. If I have a cup of lemonade and I pour out half of that lemonade, the volume is half of what it was before, but the concentration is no higher than it was. If I decrease the volume of a gas, though, then that would increase its concentration, but it wasn't a gas. So this is not going to make any impact. It didn't change the concentration at all. B, decrease the concentration of the ethanoic acid. If I decrease it, then that would make the rate go slower, not faster. And we want to increase the rate. So it's not going to be that one. Decrease the temperature. That would make it go slower too. The lower the temperature, the slower the reaction. The higher the temperature, the faster the reaction. So processes of elimination, we have D, but this also makes sense. Decrease the particle size. If we grind it up, we expose more of those atoms, the surface area of those atoms, to be able to react. Where if they're stuck in the middle of the clump, then they're not going to be able to react. So by decreasing particle size, we increase the overall surface area that's exposed and is capable of reacting, and that increases the rate of a reaction. Okay, here's my rate law. So rate is equal to K. M must be a first order, and then N is second order. So the rate of a certain chemical reaction between substance B and D obeys the rate law above. The reaction is first studied with M and N each at 1 × 10⁻³ molar. In a new experiment, if a new experiment is conducted with M and N each being 2 × 10⁻³ molar, the reaction rate will increase by a factor of what? All right, so I'm going to rewrite this rate law. Rate is equal to K, concentration of M raised to the first, concentration of N raised to the second. Okay? We doubled the concentration of both of these things. We went from 1 × 10⁻³ to 2 × 10⁻³. So this concentration is double what it was before, and this one is double what it was before. But the impact of that doubling is not the same for both, because M is first order, so it'd be like 2 raised to the first, which is 2. And then N is second order, so 2 squared, which would be 4. So 2 times by 4 is 8. The rate would actually be 8 times as much as it was before if the concentration of both of these things were doubled. 34. We want the rate law for this reaction, X plus Y turns into Z, and we had to get it from this experimental data. Okay, so we know that it's going to be rate is equal to K, concentration of X raised to something, concentration of Y raised to something. It's only the reactants, it's not the products. Okay? Now, with this, we need to see how changes in these concentrations impact the rate, and that will tell us what these orders are. So to figure out what's going on with X, I need to pick 2 experimental trials where Y stays the same, because I don't want this to have any impact. So if I look at trial 1 and trial 3, the concentration from 1 to 3 when it comes to X was double what it was before. And now what happened to the rate? It stayed exactly the same. It's like we multiplied it by 1, right? It had no impact. Well, what do I have to have this raised to? And that's 0. 2 raised to the 0 is what equals 1. When something is 0 order, that means I can change its concentration, but the rate doesn't change. So X is 0 order. Reminder, anything that's 0 order, we tend not to write down in the rate law because it just equals 1. And so from that alone, I already know my answer is B because it's the only one that doesn't have X. This is X as second order. This is X as first order, second order, and first order, not as 0 order. Now, what is Y? Let's check. I need to pick 2 rates where X stays the same so that it's not impacting this change in the rate. So that would be trial 2 and trial 3. So going from trial 2 to trial 3, I see that my concentration is half of what it used to be. Okay. Now, what about the rate? Now, it's hard to tell. If you do the later trial divided by the earlier, it will tell you what that multiplier is. So here's my later trial rate. And I'm going to divide that by my earlier trial. So this is 0.25 or a fourth. So when we halved the concentration, the rate was a fourth of what it used to be. So this had to be second order then, because 1/2 squared is equal to 1/4, and that is consistent with our answer of Y being second order. Okay, 35. If 87.5% of the sample of pure iodine decays in 24 days, what is the half-life? Now, a reminder, half-life is how much time it takes for half of a radioactive substance to decay. So, like, if I started with 100% at time 0, at half-life of 0, I got to 50% at half-life of 1. Okay, and we're saying that 87.5% has decayed. Okay, and this is where 50% has decayed. Now, if I have another half-life, then half of what was remaining decays. So we're left with 25%. Okay, so here, let's do percent decayed. If I'm at 100%, 0% has decayed. If I'm at 50%, 50% has decayed. If I'm at 25, then 75% has decayed. Half of 25 is 12.5. And if you do 100% minus 12.5, that leaves you with 87.5% of it has decayed, leaving you with 12.5% of the original. So that means it's going to be 3 half-lives to get to that percentage. And this happens in 24 days. The other important thing to note is that 24 days, each half-life is the consistent same amount of time. So if I do 24 divided by 3, each half-life had to have been 8 days. So this was day 0, this was day 8, this was day 16, and that is day 24. So each of them had a half-life of 8 days. Okay. We have a graph to the right, and I guess it's the left, shows the results of a study of the reaction of X with a large excess of Y to yield Z. So we have X plus Y yields Z, and we know that this is the excess and this is the limiting. All right, great. The concentration of X and Y were measured over a period of time. Okay. The amount of Y is not really changing because it's excess. Like, we just have so much of it that we're not tracking any, like, little change in it. Now, y, on the other hand, though, is decreasing over time. So if x was 0 order, and we had a concentration versus time, it wouldn't be curved like this. It would have been negative slope, but it would have been linear. That's 0 order. So I know that's not 0 order, okay? When it's concentration versus time, and it's first order, we get a nice curve. And we see this consistent half-life that we've talked about before. Let me find a sticky note. Okay, so we started at 20, or 0.2, and then half of this is going to decay in some amount of time. So the 0.2 is going to become a 0.1. And this took 1 hour for that to occur. Now, this is 0.1, but half of 0.1 is 0.05. So to go from 0.1 to 0.05, 0.1 to 0.05, it took the exact same amount of time, 1 hour. This consistent amount of time for half to be gone and for half to be gone, that is only true for first order. When it's second order, and it's a concentration versus time graph, the decrease is way too steep for that to work. We don't get the consistent half-life like that. And so that tells me that X is first order. Okay, 37. Nitrogen monoxide and O2 gas react to form NO2. The rate law of the reaction is rate is equal to K. NO2 is second order, O2 is first order. If the reaction occurs in a single elementary step, so this is not a multi-step, it's a single step. Well, if it's a single step, then that single step is the slow step. And a reminder that slow steps are the rate determining steps. Whatever the coefficients are in front of the reactants on the slow step, that's the order of those reactants in the rate law. So where rate is equal to K concentration of NO, that means we need to find an elementary step, a reaction, where we have a coefficient of 2 in front of the NO and a coefficient of 1 in front of the O2. That's the only one, but that's the case. 38. Which of the following best helps explain why an increase in temperature increases the rate of chemical reaction? In order for a reaction to occur, 3 things must happen. Reactant particles must collide, but collision is not enough. They must collide with proper orientation and sufficient energy, and those are our 3 things. So if I increase the temperature, now these particles are moving around faster. So of those 3 things, we've impacted 2. One is the collisions. So if they're moving faster, we simply get more collisions. It doesn't change the orientation of those collisions, but it does increase the energy of those collisions. So we need to address both of those things when we're talking about temperature. So if we increase the temperature, at a higher temperature, reaction have a lower we haven't impacted activation energy at all, that minimum amount of energy needed for a reaction to occur. So those are not our answers. At high temperatures, every collision results in the formation. No, not every collision. There's more likely to, but not everyone. At high temperature, high energy collisions happen more frequently. Yes. Okay. 39. When free Cl gas atoms encounter O3 gas molecules in the upper atmosphere, the following reaction mechanism is proposed to occur. So then we got 2 steps here. It gives us this overall. This is the slow step. This is the fast step. Okay. Whenever you're figuring out rate law from elementary steps, I want you to first identify the intermediates. Now, intermediates are made in an earlier step and consumed in a later step. Intermediates cannot be part of the rate law. So like, I know this can't be my answer because it has an intermediate in it, okay? Then after you do that, you need to find the slow step. And you're going to write the rate law of the slow step. Rate laws only consider the reactants, not the products. Okay? And whatever the coefficients are, that's their orders. So both of these had coefficients of 1, so that means both of these have orders of 1. So that means the correct answer is B. The rate law of the slow step is the overall rate law. This is the rate law of this whole reaction, of this overall reaction. Okay? The rate law of the slow step is the rate determining step. That is the rate law of the whole thing. Intermediates cannot be part of the rate law, so as long as neither of those are the intermediate, then we're done. Then we don't have to do any further steps. That's our answer. Same thing here, so number 40. We have our different steps here. Sorry, I just noticed, I was looking at this. I don't think there's supposed to be an equal sign here. I'll try to fix that on yours before I print it. And then I'm guessing this is a fast step. We only have one slow step. That must be a fast step. Okay, I'll fix that. Now, if you are writing the rate law from elementary steps, the first thing I need you to do is identify the intermediates. Now, reminder, intermediates are made in an earlier step and consumed in a later step. So that's an intermediate, and this is an intermediate. Okay, intermediates cannot be part of the rate law, so that's why I want to circle them to make sure that I can check in my rate law and see if they're there. Then you go to your slow step, and you write the rate law of the slow step because the slow step is the rate determining step. Whatever the rate law is of the slow step, that is the rate law for the whole reaction. So rate is equal to K, and then you'd put the reactants. So it's going to be concentration of not the products, the reactants, HBr and O2. Whatever the coefficients are, that's what their orders are. So this is a coefficient of 1, this is a coefficient of 1, so they're both first order. Neither one of those is an intermediate, so that means we are done. The rate law of this slow step is the overall rate law. That's our answer. Great. I was trying to see if I asked a question where we had an intermediate, but it doesn't look like I did. So I'll make sure I review that with you guys. Okay, 41. Nowhere does it tell me that this is a catalyst, but you need to know what a catalyst does. And what a catalyst does is it grabs onto reactants, it orients them in the proper way so that they can then react and become a product, and then it lets go of them. So the rubidium is here, and it grabs the nitrogen and it grabs the hydrogen, and then it pushes them together to make this product, and then it lets go of them. The rubidium is there in the beginning, it's there in the end. It's not part of the reaction, it facilitates the reaction. It helps the reaction proceed. And the way that catalysts do this is by lowering the activation energy. When they're held in proper orientation, they don't have to collide with each other with nearly as much energy. So as soon as I recognize that rubidium is a catalyst, then I bet my answer is lower activation energy. So based on the information, which of the following provides the best reason for the use of rubidium? It lowers the activation energy. It makes the reaction go faster because it's a catalyst. Number 42. Which of the following phase changes involves the transfer of heat from the surrounding to the system? Okay, so I need to start off with something that has, so from the surroundings to the system, so something with lower energy first, and it's got to become higher energy. And because that energy has to come from somewhere, and it comes from the surroundings. It's going to go from the surroundings to the system. So it involves the transfer of heat from the surroundings to the system. Okay, so starting off lower, ending up with higher. So the first one is a gas to a liquid. Nope, that's the opposite. That's a higher energy to a lower. B is a gas to a solid. That's even more so a higher to a lower. C is a liquid to a solid. Nope, that's a higher to a lower. Let's see. And I need a lower to a higher. That's only D. Liquid to a gas. So liquid is lower, and then gas is a higher energy, so then the answer is D. Okay, number 43. A hot iron ball is dropped into a 200-gram sample of water initially at 50 degrees Celsius. If 8.4 kilojoules of heat is transferred from the ball to the water, what is the final temperature of the water? Okay. They're giving me a specific heat, and I know that all of this heat, letter Q representing this, that is lost by the iron, it's exactly equal to all the heat that was gained by the water. Okay? Now, something important to note, though, is I would inverse the signs, though. Like, this would be negative because it's losing the heat, and this would be positive. The other thing I know is Q is equal to mc delta T, our MCAT equation. Mass, specific heat, change in temperature. This specific heat tells me the units that I'm wanting to work with here. So my energy is going to be units of joules, I want mass in grams, and I want temperature in Celsius. So a hot iron ball is dropped into a 200-gram sample of water. So I know my mass of water, 200 grams. Initially, so temperature initial for the water is 50 degrees Celsius. If 8.4 kilojoules of heat is transferred from the ball to the water, so the heat of the water is a positive 8.4 kilojoules. This is in joules, so I'm going to change that. I'm going to times it by 1,000, so it's going to be 8,400 joules, because I want all those units to be the same as my specific heat. What is the final temperature? So temperature final. And then our specific heat is 4.2 joules per gram degrees Celsius. Great. Let's rearrange to solve for delta T first. So Q divided by MC equals delta T. And delta T is temperature final minus temperature initial. So to get temperature final, I'm going to add temperature initial to the other side. So Q divided by M multiplied by C plus the initial temperature will equal the temperature final. So I take that heat, which is 8,400, and I'm going to start by dividing it by the mass, 200, times by the specific heat, 4.2. Okay, so that's what I got right here. But now I need to add the temperature initial, so plus the 50 degrees. So my temperature final is 60 degrees Celsius. Number 44. Which of the following questions the following question refers to the graph to the right, which shows the heating curve for methane, how much energy is required to melt 64 grams of methane. Okay, so first off, you need to understand these phase change graphs. So we start off as a solid, and it's a solid this whole time, but it's increasing in temperature, and then we get to a plateau, and that's a phase change. So this is from solid to liquid, so that means this plateau right here is melting. This is the delta H of fusion, the amount of energy added in order to melt something, or the amount of energy lost to freeze something. Then this is liquid, 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 and now we're vaporizing. So this is the amount of energy it takes to add to a liquid to turn it into a gas, or energy that is lost when we condense, when we go from a gas to a liquid. And we are melting, so we're concentrated on this guy. It is 0.94 kilojoules per mole. And so I have 64 grams of CH4. Carbon has a molar mass of 12.01. Yeah. Hydrogen is 1.008, but there's 4 of those. So we get roughly 16 grams per mole. 64 divided by 16 is 4. So we're dealing with 4 moles of methane, right? But guess what? It's 0.94 kilojoules per mole. So each one of those moles per mole is 0.94 kilojoules. So 4 times by 0.94, that means we get 3.76, which is essentially 3.8 kilojoules. All right, 45. What is the amount of heat released when 4 moles of H2S reacts with 9 moles of O2? Okay, we got an option here. We can do a BCCA table, or to figure out which one's the limiting, which one's the excess. Or we can do 2 shorter goalposts and see which one releases more energy, which one releases less energy. So let me explain. If I have 4 moles of H2S, how much heat is released? Well, for every 2 moles of H2S, this is how much heat is released, okay? So like if I start with 4 moles of H2S, for every 2 moles of H2S, we release 1,120 kilojoules, okay? So 2 times by that guy. So we're releasing 2,240 kilojoules of energy. If 9 moles of O2 reacts, for every 3 moles of O2 that reacts, we release the 1,120 kilojoules. And so then that would mean we release negative 3,360 kilojoules. But it turns out there's not enough H2S to produce this much heat. There's only enough H2S to produce that much heat. That makes H2S the limiting, and so we only produce that many kilojoules, not that many. And 46. Bond enthalpies. Okay, bond enthalpies are opposite from what we like it to be. Like we're so used to it being products minus reactants, but bond enthalpies are reactants minus products. They're the energy of the bonds broken minus the energy of the bonds formed. So we have 2 H2O2s. So here, okay, I'm going to draw this Lewis dot structure. Now, each of these oxygens have 6 valence electrons, so 1, 2, 3, 4, 5, 6. But there's 2 of these guys. And this is going to turn into 2 water molecules. And an O2. A reminder about my little trick when it's a diatomic molecule. So if I have 2 atoms that are bonding together from group 17, they're going to be single bonded. 2 atoms from group 16 are a double. 2 atoms from group 15 are a triple bond. Okay. So if I want to take the sum of the energies of the bonds broken, let's do that first. So here's the ones that are being broken, here's the ones being formed, right? There is 1, 2, 3, 4 hydrogens single bonded to oxygens, right? 1, 2, 3, 4. So I have 4 of those hydrogens single bonded to oxygens, 463 kilojoules. And then I also have 2 of these oxygens single bonded to oxygen, 146 kilojoules. So there, when I add all those together, that's the sum of the energy of the bonds broken. And then I need to subtract this from the sum of the bonds being formed. So this is 1, 2, 3, 4. So I have another 4 oxygens single bonded to hydrogens. And then I need to add that to 1 oxygen that's double bond, like 1 double bond for the oxygen, 495. Okay, so 2 times by 146 minus 495, negative 203 kilojoules. When I plug all that in, that's how much energy is released during this reaction. It's exothermic. Okay, 47. If the standard molar heat of formation of ammonia and gaseous water are negative 46 kilojoules per mole and negative 242 kilojoules per mole respectively. Okay, so we said ammonia and then we said water. So the ammonia must be negative 46 kilojoules per mole, and then the water is negative 242 kilojoules per mole. What is the value of delta H? So not delta H of formation when it comes to bond. It's not bond energy, it's energy of formation. So to get this delta H of the reaction, we can take the sum of the delta H of the products and we minus it from the sum of the delta H's for the reactants. When it comes to delta H of formations, when something is in its pure elemental form, its energy, its enthalpy of formation is 0. So 3 times by 0 is 0, 2 times by 0 is 0. For the remainder of this, though, my products, so I have 6 moles of H2O, and each of those moles was a negative 242 kilojoules. Okay? And then I'm not going to do the 2 plus 2 that are 0, and I'm going to minus that from my reactants. 4 times by negative 46 kilojoules. Same thing, I'm not adding in the 0 there. Plug this in my calculator and I get negative 1268 kilojoules, which is closest to my answer option D there. Okay, 48. Here is my steps. This is my overall. So in my overall, there was 2 O3s on the reactant side. And guess what? There's 2 O3s on the reactant side in step 1. So that doesn't need to be present in step 2. But what is in the overall that is not in step 1 is 2 nitrogen monoxides on the reactant side. So they have to be present in step 2. I must have at least these 2 NO gas right there. So that way it can show up. As far as the product side goes, there are 2 NO2 gas, and that's not up here, so it must be there. And then we have 2 O2s, but that's 3 O2s. So one of them had to cancel. So what if we put an O2 right here? Right? If I put an O2 right here, then this can cancel with one of those, and I can be left with 2 O2s. Okay? So double checking, this would cancel, left with 2. So we get this guy, we get that guy, this one. Yeah. All right, great. So what is this reaction to? What could that be? And it is C. 49. According to the information above, what is the standard enthalpy of formation for NH3? And then we have our delta H of the whole thing right here. Okay, when something is in its pure elemental form, like H2 and N2, their delta H of formations, their enthalpy of formations are 0. Now to get this delta H of this whole reaction, this 92 kilojoules, you would add together the sum of the enthalpies of formation for the products, and you would minus it by the sum of the enthalpy of formation of the reactants here. However, both of my products are going to equal 0. So we get this 0, and then we're going to minus it from 2 times by this formation that we're trying to solve for, the delta H of formation of this guy. And we know that this answer is 92. So 92 is equal to -2 times by the delta H of formation there. Okay, great. If we divide by a -2, that's going to equal this formation that we're solving for. We get -46 kilojoules. That's our answer. All right, 50, last one. Okay, so these are the individual steps. This is my overall reaction. And we can see that it cancels out to give us this. That I have 2 Cl gases on the product side, and then I have 2 separate Cl gases on the reactant side. I have a hydrogen gas on the product and the reactant side. I think that's it. And so then I'm left with H2 plus Cl2, and that's going to produce 2 of these HCl's. So I didn't multiply any of these. I didn't flip any of them. When it comes to delta H, it's like all the others. The one that's different is our K values. Delta H is not different. When we add together a reaction, we add together the delta H's. So to get the delta H of this overall, I will add this delta H plus that delta H plus that one. So I'm going to take 242 plus 4 plus the -432. So this reaction has a delta H of -186 kilojoules. Now here's where this question is tricky and most students miss it, is what is the value of enthalpy, so the delta H, change per mole of HCl, and we are ending with 2 moles of HCl. So for every 2 moles of HCl that's produced, this is how much heat is released. So if we divide that by 2, then this is how much heat is released for a single mole of HCl. Okay, well done.